Okay, so continuity. So what is the definition of continuity? We say f is continuous at the point x equals c. So remember, being continuous is a property at that point. If what? So what is the definition of continuity? What condition has to hold for a function to be continuous at x equals c? So you guys should have seen this in the videos. Okay, so I think people are listing. Let's see. So there's actually one condition that really defines continuity, but you can think of this as three separate conditions. That's a lot of sometimes how textbooks will kind of simplify that presentation. So it looks like that's what students are giving me in chat. So it looks like a few people said, okay, f of c has to exist, or if that's definitely required. The limit exists, the limit of f of x. Okay, so the limit as x approaches c of f of x, that also has to exist. Okay, so that exists, and that also has to be equal to c. Right, and really, I only really need to list that last condition. The reason why this last condition is really the only one you ever have to list is because it implies the other ones, right? When we have an equation and we say two things are equal, that implicitly means that the two things exist in the first place. But a lot of times textbooks and videos will kind of spell that out explicitly so that you don't forget. So yeah, so this equation implies that both the function value and the limit both exist, and then the true condition for continuity is that those two things really have to be equal to each other. So we used to call this the direct substitution property. I probably will still call it that from time to time. So that is f has the direct substitution property at x equals c. And if any of these conditions is true, so if this equation is false, and it can be false if any of these three conditions fails to be true. And so in that case, we just say f is discontinuous. Okay. So let's talk about how can a function fail to be continuous, right? What does it mean, if a function say fails one of these conditions, but it maybe satisfies some other conditions. Um, I will say if it fails one of the first two, it automatically fails the third one, right? So I can't have like minus plus plus, but I can have something like this, right? It fails the first and third conditions, but it satisfies the second condition. Like, what does that actually look like on a graph? So there are actually four types of discontinuities, um, depending on which conditions are actually satisfied. How can a function fail to be discontinuous or fail to be continuous? Okay, so there are four types of discontinuity. So, can someone can someone describe at least one type of discontinuity graphically? Like when you think of a discontinuous function, what are you thinking of graphically? What jumps out at you? Okay, so let's see. Kyle and Isman, they both gave us two examples. Um, so Kyle said a jump, and we will get to that. That's the second example that I wrote in my notes. So we have a jump discontinuity. In fact, that's actually what it's called, a jump discontinuity. And then it looks like everyone else is saying a hole in the graph, and those are actually called removable discontinuities. So let's look at that first. So a removable discontinuity is something that's like this. Possibly there is a closed hole there, but the idea is that it's not where it should be, so to speak. So this is called a removable discontinuity. And why is it called removable? The reason why it's called removable is because it is possible to say, okay, well, the function value in this case is, say, f of 2 equals 3. If I were to redefine the function, if I were to say, you know what, I don't like that function, I'm going to define a new function that is the same as the old function, except f of 2 is equal to 5, well, now the discontinuity is removed. So you can, in other words, you can remove the discontinuity by simply redefining a one function value. So which conditions are actually satisfied here? Um, let's see. So f of c may or may not exist. Right, whatever. But the characterizing feature of removal discontinuity is that the limit, what can you say about this limit? Limit as x approaches c of f of x. What would you say about that limit? What is the defining feature of a removable discontinuity? It exists, right? That is the that is the characterizing feature of removable discontinuity. That the limit exists, but obviously since it's discontinuous, it would have to be the case that it is not true that that limit is equal to the function value. So the limit exists, but is not equal to the function value. So there was a question on the exam, the very first question, second question actually, that asked you to identify all x values such that this was such that this was true. The limit exists, but that limit is not equal to the function value. And it turned out to be a pretty challenging problem. A lot fewer people got it right than I thought. But now you can go back to it with this knowledge and realize, okay, that actually just means you're looking graphically for a function that just has a hole in it at one little point like that, right? No jump, but just a hole in the graph. So now you know graphically what to look for. All right, number two, we have a jump discontinuity. So this was already mentioned. That's something like this. And how would you describe a jump discontinuity precisely? What would you say is the defining feature of a jump discontinuity? Yeah, something about piecewise, right? Can we say a bit more precisely? How would you describe this in terms of limits? So f of c, again, may or may not exist. I don't really care what the function value. Limit of f of x does not exist. That is true, but there are other ways. Is it just the limit doesn't exist? Because, for instance, if I had an asymptote and vertical asymptote, that's also a case where the limit doesn't exist. But that's not a jump discontinuity. What is particular about a jump discontinuity? What do you think? The two limits do not equal each other, right? Exactly. So the left and right limits exist, but are not equal to each other, right? So in particular, this does mean this does mean that the limit as x approaches c does not exist. Okay. And then the third type of discontinuity we've seen, actually just mentioned this, right? An infinite discontinuity. And so that's a case where I have a vertical asymptote. And I don't need to have it on, or I can just have an infinite limit on at least one of the two sides. Yeah, pole. If you read my notes, sometimes this is also called a pole. In more advanced mathematics, actually what I've drawn here is actually not a pole. But in more advanced mathematics, if you have certain types of infinite discontinuities, they're also called poles. And so the defining feature here is that one of the two sides has an infinite limit. And again, the function value may or may not exist. Now, the last type of discontinuity, so you may think that those three examples kind of exhaust everything. It turns out not. And there's something called an essential discontinuity. This type of discontinuity, you did not see in the videos, and you probably won't see again in this course. It's a pretty difficult discontinuity to kind of describe precisely, or at least give precise examples of it. Um, all you have to really know is if, say, for instance, I have a function that exhibits infinite oscillation near a point, I get this essential discontinuity. So an example of this, if you want to look, is something like sine of 1 over x. That has infinite discontinuity at the near x equals 0. The actual definition of essential discontinuity is it's kind of boring, not one of the other three. The function is discontinuous, but it does not satisfy any of the previous conditions. It's not removable, it's not infinite, it's not a jump. The reason why it's not a jump because it turns out with these essential discontinuities, the left and the right limits actually don't even exist individually. So, anyways, um, now at this point we actually have discussed the three main types of discontinuities, right? Last week we just when we started limits, we discussed removable discontinuities and we discussed jump discontinuities, right? Jump discontinuities occurred a lot with piecewise functions, and these removable discontinuities occurred a lot when we had a 0 over 0 form, right? And then just earlier this week on Monday, we discussed finally the infinite discontinuities and essential, which is skipping. It's too hard. All right, example number one.